Now, in order to test this hypothesis, we are going to need a new test statistic. That's going to be called the chi-squared test statistic, and it measures the amount of disagreement here between the data, the observed data, and the null hypothesis, the hypothesized proportions. And it's defined to be O sub I is the first observed count, and E sub I is the first expected count. So it's the difference between what you get and what you expect to have from the null hypothesis. We square that to make everything positive so we don't get any canceling. And then we divide by the expected. So this is a relative amount. And then we sum all those up. So the more that O sub I difference from E sub I, the observed from the expected, the bigger this sum is going to be, the bigger chi-squared is. So a bigger chi-squared is more extreme. And these expected counts is the total number of observations times our hypothesized proportion. That's what we would have as the expected value for each category that we're considering. So this test statistic, this chi-squared test statistic, follows a skewed distribution. Looks like this. There's actually a different distribution depending on how many observations total you have and then how many categories you have. So it varies with your degrees of freedom, which are defined to be k minus 1, so 1 less than the number of categories. And then also the total number n. So a typical chi-squared distribution would look like this. So let's use our calculator here to find some chi-squared test statistics or chi-squared probabilities here for some given degrees of freedom. So we want to find the probability that chi-squared is less than 3.88 with degrees of freedom 10. So that 3.88 would be somewhere along the bottom here. Say it would be maybe right here, 3.88, and then chi-squared less than 3.88 is going to be the left area here. So that's what this is finding. So if you grab your calculator here, we want to go to second variables, our distribution menu, and then you see chi-squared PDF and CDF. You want CDF, which is number 8. Our lower, the chi-squared distribution starts at 0, so your lower is always 0. Our upper is 3.88, because we want the area between, this is 0. 0 and 3.88, that's what that probability is. Probabilities are areas. Our degrees of freedom here are 10. Paste it, and 0.0474. So this would be 4.74% of the area. Total area underneath any chi-squared distribution curve is 1 or 100%. So this is not drawn to scale, obviously. Probability that our chi-squared value is greater than 10.55. So now greater than is going to be right area. So this would be 10.55 and then to the right. That's going to go up to infinity. Degrees of freedom are 15. So we will go to our distribution menu again. And again, we want number 8, cumulative distribution function. We are starting at 10.55. We're going up to infinity. We'll just use 10,000. And then our degrees of freedom, again, we're given as 15. Paste it, 0.7838. So approximately 78% of the area is to the right of the critical value 10.55. So that's how you find areas if you're given the chi-squared value. Now, lots of times in hypothesis testing, we're given the area, we want to go back and find the value of the test statistic, well, the critical value, right? So we're going to do that. You can't do that on your calculator. It does not have an inverse chi-squared distribution. but I did program functions in Excel, the Excel distribution calculator, and it's going to be the inverse chi-squared tab. So that is available in Canvas. It's in the student files folder. So here is the distribution calculator. I've opened it up. I clicked on the inverse chi-squared tab. And what we want to compute here first is chi-square 0.01 for degrees of freedom 7. So 0.01 is the right area. So just like when we did z sub alpha and t sub alpha values. So if we look here, our degrees of freedom, we've got alpha, and then we've got our degrees of freedom. So 0.01 is our alpha. Degrees of freedom here, again, were 7. And then we want the right tail or the left tail critical value. So left tail would be 0.01 to the left, and right tail would be 0.01 to the right. So our area is the number C, and this is saying right tail means x value greater than the chi-squared critical value is equal to that area. So we want the 18.475. So this will always be right area, the subscripted. Chi-squared 0.95 for degrees of freedom 12. So this means the right area is 0.95, so the left area is 0.05. So that'll be 0.95 here. And then our degrees of freedom again, 12. And we want right-tailed area again here, 5.226. So that's how you find chi-squared critical values. So if we use the distribution calculator for these, then you won't need to use tables in the book. So that's a big plus. So the rejection regions for the chi-squared test have the form chi-squared has to be greater than chi-squared sub alpha, with degrees of freedom is k minus 1. So what we're doing here is we're finding cutoffs for the rejection region for the test. And then lastly, we want to actually find the rejection region for a chi-squared goodness of fit test with a null hypothesis P1 equal P2 equal P3 all the way up to equal PK. So that's saying all the proportions are equal. All of the counts should be equally likely. So that's one form of null hypothesis. And in part A here, they give us k equals 5 and alpha is 0.01. So that is saying that we've got 5 proportions, 5 categories. And remember here our degrees of freedom are k minus 1. So degrees of freedom here will be 5 minus 1, which is 4. And we want the critical value chi-squared 0.01. So your subscripted number, that's your alpha. So degrees of freedom 4, chi-squared 0.01. So we'll go to our distribution calculator again. 0.01 for our alpha. And degrees of freedom 4. And again, we want right area. That's right-tailed test, 13.277. And I'm saying right tail here because the rejection region for chi-squared test is of the form chi-squared greater than a critical value, which is right area. So it'll be a right-tailed. If k is equal to 10 and alpha is 0.05, that's saying that our degrees of freedom here are going to be 9. And we want chi-squared 0.05 now. So go back to the distribution calculator. 0.05 for alpha, degrees of freedom 9, and then our right-tailed area 16.919. So that's finding areas under the curve and then finding critical values and cutoffs for the rejection region.